Hey everybody, this is our probably our last installment of a class lesson in for probability section. And we're going to be talking about expected value. So the expected value is whether we're talking about gambling or investing, it talks about what's going to happen on average over the long term. And clearly positive EV means that I'm going to earn more than I have to invest. The payoff is going to exceed whatever the cost is. I can also have negative EV, which is bad, which means whatever the cost of the investment or the game is, the payoff is less than the cost, right? So our formula for the expected value is straightforward. For all of the events in the set, right, we have outcomes, x sub I, times the probability that outcome occurs. And we sum this up over all possible I. All of the outcomes have a probability. We multiply those together and we sum the products for every single outcome in the probability space. And that's what it means. We say it's the average or the expected value of that probability experiment happening over and over. This is a lowercase mu, the Greek letter mu, and mu sub x is the average of x, often referred to as the mean of x as we start transitioning into statistics for the second half of the semester. Okay, we also have formulas for the variance and the standard deviation. So the variance, please notice, is the expected value of x squared. So I take all the outcomes and square them. So if the first outcome, the original outcome is 4, I square it and I get 16. And it's the same formula as expected value, but with all the outcomes squared. Not the probabilities, just the outcomes. And then I subtract the square of the expected value, or, right, mu sub x squared, right? So I've written the formula that way here so that you can see what's going on. Then the standard deviation is the square root of the variance. Now, you'll notice that I wrote it the easy way. Sigma squared equals the variance. However, you can't generally do this. Why? Well, because often square roots can be positive or negative, and then I have to specify which one I'm dealing with. But it turns out that both the variance and the standard deviation are always positive. And since they're always positive, I can use this shorter way, this sigma squared equals the variance. Again, this is the lowercase Greek letter mu, and over here we have the lowercase Greek letter sigma. Sigma has some advantages, or the standard deviation has some advantages over the variance. The main one is that it's in the right units. It's in the same units as the original data. So imagine that the expected value, imagine the original data, the outcomes are in dollars. And the expected value, the average is in dollars. Okay, and then the variance is in dollars squared, right? If you think about what's going on, right, I'm squaring all the outcomes, so all the units are squared, right? So the variance is in dollars squared, but the standard deviation returns to the same units as the original data. So it's a big reason that we prefer it, especially when we get into statistics, but also in probability. Okay, and again, the long-term expectation, that's what we mean by expected value, that if we repeat the probability experiment over and over and over and over and over, the expected value is what we will see happen on average over the long term. And be careful because expected values can be negative. The variance is going to measure the dispersion, or how far these outcomes scatter. Now it's a weighted average, so outcomes that are more likely more heavily influence the variance. So that's something to know. And as I said before, we generally prefer the standard deviation over the variance. And kind of the key thing to help you understand what's going on with expectation and variance is thinking of these games like the lottery, thinking of these Vegas games like a slot machine, where there's each lottery ticket, each time you play the slot machine, it's only a small amount of money that you have to invest. And it's negative expectation, but the payout can be huge with the lottery, or let's just think of playing quarter slot machines. And yeah, every time you put a quarter in, you're pretty likely to lose it, but it's only a quarter. And then if you hit a jackpot, you're probably going to win 200, 300, $400. Okay, so yeah, there's that negative 25 cents of expectation for each individual play, but the win can be huge. And even if I put $10 or $20 worth of quarters into the slot machine, if I hit the jackpot, the cost to play was very small in comparison to the big payoff. And that's why with these games of chance that normies like to play, they tend to have a small negative expected value, but a huge variance, a huge standard deviation to allow for that big win that generates excitement in the game. Okay, so let's take these ideas and actually calculate some expected values for some simple situations. So the first situation is we're going to roll a fair six-sided die, right? And so the possible outcomes are 1, 2, 3, 4, 5, and 6, and it's a uniform distribution, so all those outcomes are equally likely. So the probabilities are 1, 6. So you'll notice what I'm doing. I'll take the outcome of 1 times the probability that it occurs, right? The outcome times the probability. Outcome of 2 times 1, 6, outcome of 3, outcome of 4, outcome of 5. So I just take all of the outcomes times the probability that that particular outcome occurs, and then I sum all the products. And in this case, you can see that 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals 21 over 6. Okay? And let's jump into our notebook. And let me get rid of the red marks. And as we scroll down here, yes, I have the definitions and a few of the notes. So what are we doing? All right. So our expected value, right, is going to be, right, the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. And I have to print out EV at the bottom there. So I get the EV of 3.5, which is exactly what our calculations lead to believe, right? So remember, I can do the sum of 1, 2, 3, 4, 5, 6 in R by doing this colon. 1 to 6 will list the numbers, the integers, 1, 2, 3, 4, 5, 6, and then I can take the sum of them. All right, well, that was easy. And 3.5 is the expected value for a dice roll, which makes sense, right? It seems to be towards the middle, between 1 and 6, right? It's close there to the middle. So that one makes good intuitive sense. All right, and again, remember, we'll call this the mean of the dice roll. 3.5 is the mean of the dice roll, mu sub x. Okay. And remember that variance is the expected value of the outcome squared. So 1 squared is still 1, but 2 squared is 4, and 3 squared is 9, 4 squared is 16, 25, 36. Okay? And let's see how to do that in R. Okay, it turns out that there is a way to find the sum of these squared values. Let's first look and see, right? If I do 1 colon 6, it prints out the values 1, 2, 3, 4, 5, 6. And the important thing to notice here is that it's a vector. It's a row vector. Why is that important? It's important because that will allow us to do this vector squared. And the way R works on vectors when I square it is that it squares the individual terms rather than actually multiplying the vector times itself, like a dot product or something, or a cross product, whatever. It actually just squares the individual items in that vector. So if I want to do like, okay, the variance is equal to what? Well, it's the sum of the values from 1 to 6 squared times those probabilities, which again, 1/6 is each of the probabilities. So I can take this sum and put it over the common denominator and print that out, and I get 15 and a sixth, 15 and 1/6. Okay, so let's check this out, and that's exactly what we get when we use a calculator or a spreadsheet or whatever machine we're using to help us add all this up. And so that's the expected value of x squared. That's only the first term, though, right? I have to take and subtract this last term. Wait, I'm sorry, that's not the last term. This is the last term, sorry. And when I do that, right, I'll have the 91 over 6 subtracted off, and I need to subtract the 3 halves squared, 7 halves squared, which is 49 over 4. Okay, so when I have 49 over 4 and 91 over 6, then 12 is my common denominator, so I'm multiplying this fraction by 2 over 2, that's the 198 and the 12, and I'm multiplying this fraction by 3 over 3, so I have 147 and 12. Then I take 182 minus 47 and I get 35. And you see how those calculations are going. All right, and it ends up with 2.9166666 repeating. Let's check that out in R to make sure that the calculations come out the same. Right, so here I am in R. And what do I need to do? I need to take this value minus 3.5 squared. Okay, and do I need parentheses? No, I don't. If you want to put them in, it doesn't hurt anything. But remember, your order of operations will evaluate the exponent before the subtraction. And 2.91667 is exactly what we see here. Right, so again, just showing you these tricks in R that allow us to do these calculations quickly if we're using R in the Jupyter Hub as our method of calculation for probabilities. Okay. And what's next in here? We're going to look at roulette. Sorry, jump here in the PowerPoint to roulette. And sorry, you'll see all of these. Oh yeah, I forgot to get the standard deviation. I got the variance up here, right? But the standard deviation is going to equal the square root of the variance. And if I print that out, that'll be 1.708, right? 1.7078, which, as you'll see, matches this here. All right, so, and then we have a nice summary. Right, these are the values we got. The expected value is 3.5. The variance was 35/12. And then the square root of that is the standard deviation, which is 1.70, approximately 1.70783. Excellent. Okay. So roulette, if you're not familiar with it, there are 36 numbered slots that are black and red typically. And there are 2 green slots. The 00 and the 0 slot are green. And the numbers 1 through 36 are on the other slots in the wheel. So the wheel has 38 slots, and it's a uniform distribution. So the silver roulette ball that when we spin the wheel, it bounces around, and it's equally likely to land in any of the 38 slots. But that's the magic for the casino, right? Because the green slots count as part of the probabilities, right? It's just the way the machine works, but they're not part of the payoffs. Let me explain that just a little bit better. Okay, so the chance of success, if we're betting even or odd, is 18 over 38. The numbered slots 1 through 36, 18 of them are odd, 18 of them are even. So you can bet odd or even. And if you bet $1 and you win $2. If you bet $1 and it comes up the other, then you're just out your money. You make 0. Okay? So, what are we writing for our expected value formula? Well, you win positive $2 if you bet evens and it actually comes up even, and that happens what? That happens 18 out of 38 times. Okay, which reduces to 9/19. The rest of the time, 10/19 of the time, it doesn't come up even. And just because it didn't come up even doesn't mean it came up odd. It means it came up odd, or it came up 0, or it came up 0, 0. So there are 2 extra outcomes in here that lower the probabilities for a success, but the payoff pays off as though there were only 36 slots. And it pays off as 2 to 1. Okay, so what does that mean? Well, if you evaluate that, that means that for every dollar you bet on roulette, the expectation is that you'll lose about a nickel. Negative 1/19 is close to negative 1/20, which would be 5 cents on every dollar that's going to the casino's pocket rather than your pocket. All right. And how are we going to calculate that? So our expected value is going to be 2 times 9/19, right? The probability of success is 9/19 minus, and I'll put the 1 in there. It's not really that big a deal. But remember that the chance of not having a success is 10/19. What didn't it like? Oh, it didn't like not having the multiplication. Okay. And you'll notice that I'm not getting the correct evaluation, so I'm thinking about this. 18/19 minus 10/19. I will have to consider this for just a moment and get back to you. I see what I've done. I've got this backwards. Excuse me. I have the formula incorrect. Let me to explain. The times that you win $2, you've also paid $1, right? You pay $1 to play when you lose and when you win. So when you win, you get your dollar back, and it's only a +1. So I set this up incorrectly, forgetting that there's a cost for each play. So when I jump back in here, if I were just to change this, I'll get the right value, right? It's a +1. There we go. And there's the -1 nickel. I know it's slightly more than that I lose, but I lose about a nickel for every dollar that I put onto the roulette table. Sorry about that unfortunate typo, but that's the correct. And they don't ask me for standard deviation, or variance, right? They just ask me, what's the expected value. By the way, the expected value for all roulette plays is the same, whether I bet on 4 numbers, whether I bet on a single number. It turns out that those expected values are all the same. They're all negative 1/19. So the last example we'll look at is the card draw. Okay. And the question is, would we pay $2 for the chance to play this game? Well, we're going to calculate the expected value. If the expected value is more than $2, then sure, I'd pay $2 to play it. Okay, so we're going to draw a single card at random from a standard deck. And if it's a face card, we get $5. If it's an ace, we get 10. Otherwise, we just lose whatever it was we paid to play the game. And the question is $2 a good, fair price? Okay. And so we're going to calculate the expected value here. All right. So the probability of an ace is 1/13. 1 out of 13 cards in the deck are aces, and there's a $10 payoff. At the moment, notice that we don't have a down payment, right? We haven't included the $2. Why? Well, we're just going to calculate the expected value of the game as if it were free to play. And then we'll see what the expectation is and whether it is, in fact, worth $2. Okay? $5, 3/13. Well, three of the values are jack or king or queen. So 3/13. And then the remainder of the time, we don't win anything. Again, in a moment, we'll add the pay-to-play feature of this game. But at the moment, it costs $0. So the expected value, with no cost to play the game, 0 cost to play the game, is 10/13 plus 15/13, or 25/13. All right. So in terms of winning at $0 to play, of course we'd play it for free because on average, we're winning $1.92 a trial. Okay. Would I pay $2 to play that? Well, no, because generally speaking, I'm losing about 8 cents, right? And again, this is the type of game that does appeal in Vegas or in the lotteries, in the casino, as long as the expected value is pretty small and the variance is large. Now, $10 just isn't life-changing money, so I don't know how popular this game would be. But again, I lose 8 cents a few times with a chance to walk away with $10. And this is the type of game of chance that appeals to many humans. And then the standard deviation, notice what we do. We take the $10 outcome and square it, same probability as before. We take the $5 outcome and square it with the same probability as before. $0 squared is still $0. And notice that we're subtracting out the 25/13 squared. The 25/13, if you jump back one slide, 25/13 is the correct value for the expected value. So it's 25/13 squared to go in our formula. And you do some arithmetic, right? You get a common denominator. And then we end up with 1225 minus 625 is 600 over 169, which is about 3.5503. And then we take the square root of 600 over 169, and we get 1.8842 for our standard deviation. And looking back, right, so here we can do EV equals, right, 10 divided by 13, right, 10 times 1/13 plus 5 times, this is 3/15, sorry, 5 times 3/15, plus 0 times anything. It doesn't really matter here, right, but it was 9/13, right, that's what we said. And even the 0 needs a multiplication symbol, okay? So the expected value is 1.77 roughly, right? So let's look at what 25/13 is just to see if we're correct. Wow, I made an error there. Oh, I have 15ths, not 13ths in that denominator. There, everything comes out nicely, as it should. And right, so the variance will be what? Well, it's going to be this stuff squared. And I'm not bringing the 0 term in. I'm just going to... Wait, I don't need the parentheses, sorry. I need the outcome squared divided by 13, and then I need the outcome squared times 3/13. Again, 0 squared is still 0, and then I'm going to subtract the EV squared. And when I print out the variable and see what's in it, I'm getting 9.76. And when the standard deviation is equal to the square root of the variance, 3.1246. And I've made a little bit of an error, and I'm not quite sure where that occurred. Just write this as 100. And write this as 25. And the EV squared, .1246, and it's frustrating me that I either did the calculations wrong on the slide, which is possible, and because I don't see what I could be doing wrong here. So I'm going to end the video here, and sorry for the confusion. This is, in fact, right, what I've showed you here is in fact how to do it. And don't make an arithmetic error, as I apparently did. All right. Have a great day, everybody.